In this video, I'm going to talk about electric, gravitational, and magnetic fields. I'm going to qualitatively describe what a field is and how the fields are created by the forces that cause them, as well as being able to draw them. Please read the success criteria I plan to cover in this video. So let's start with describing what is a field. Well, it's a region of space in which a force is applied upon another object. So let's think about that in a little bit more detail. First of all, I said region of space and not an area, because this is in 3 dimensions. Even though we draw it on our paper in 2 dimensions, it happens in all 3 directions. So as I said in the title, I'm going to talk about electrical, gravitational, magnetic forces. They all have some similarities. They all are forces that are act at a distance, so you don't need contact between them in order to experience a force. That's what's so important about the idea of a field. So first of all, I'm going to have a very large mass right here. It's going to be causing my gravitational field. And I'm going to put a small little test mass right here. Now, it's called a test mass because it's so small it doesn't have a gravitational field of its own. We kind of imagine that. We know the gravitational force is going to be an attractive force, and it will be attracted in this direction. Now, I can put this little test mass in a lot of different places, and we know it will always be attracted towards the center. In fact, that's the whole idea of a field, is I can then predict, no matter where my test mass is, the direction that the force will be applied to it. So let me draw this in a little bit more. Anywhere along this line, it will be attracted towards the center. And here, and this part as well. So let me draw it all in for you. So let me draw in my arrows here, because no matter which part I have, along these lines, I should be always attracted towards the center of the large mass. And yes, these should be straight lines. Ignore my bad penmanship. So one thing I want to point out while we have this diagram is see out here how the lines are farther apart than in center. That means that my gravitational field is weaker out here where the lines are farther apart than when they are closer together. In other words, my force per charge acting on the test mass is weaker as the lines are farther apart. So now let's move on to electric fields. Take a look, I now have force per charge acting on my positive test charge. For the gravitational field, it was force per mass. Notice here there's a difference. I have force per charge on a positive test charge. This is one of the differences between a gravitational field and an electric field. Now, at a convention, we will always choose a positive test charge when drawing our electric fields. If I put my positive test charge right here in the region around my positive charge, we know we will have repulsion. And again, I'm using a test charge, so it's so small it does not have a field of its own. So again, just like before, I'm going to go around my charge with my little positive test charge, and I'm going to draw in the force of repulsion. And I should get a pattern that looks familiar. And again, these should be straight lines. Now let's go over here to the negative charge. So if I now put my test mass right here, instead of being repelled, my positive test charge is now going to be attracted. Instead of pointing outwards like my positive charge, now they're going to point inwards, and now it's going to look just like my gravitational field I had earlier. Let me draw in some more lines. Now, instead of considering these two independently like this, what would happen if they both were side by side? Notice that the positive charge on the left always causes it to be repelled, but the one on the right always causes it to be attracted. So if I put my positive test charge right here, it's going to be repelled from the left and attracted to the right, so in fact I could just extend this line. Now if I put my positive test charge right here, it's going to be repelled from the left upwards and also to the right. Now I think about from the negative charge, it's going to be attracted down and to the right. Now the forces are vectors and I have to add them together as such, and I'd actually start to get the line looking like this. Similarly for the bottom. Notice here at the top it's a flat line. That means the repulsion from the left and the attraction from the right, up and down, cancel out, and I just have a net result to the right. Now one more thing, this line here, which was straight up before, is probably going to bend a little bit inwards because now I've got a bit of attraction that wasn't there before. In fact, all of these lines would slightly bend around. Finally, magnetic fields. Let's think what we'd be looking for here. Well, now we're going to be looking for the force acting on a test pole. And instead of having a test mass or a test charge, we have these little wee plotting compasses. They're usually around the size of a Smartie, or less than 1 centimeter in diameter. And you should be able to tell me why we have to use something like that. So it doesn't have a magnetic field of its own. And just like with the electric fields, we always talked about the direction on the positive test charge. Now with our plotting compass, we always have to say we're looking for the direction that the North Pole on my little test compass is going to point. So if I put my little test compass right here, I would have its North Pole being repelled by this North Pole and its south end being attracted. So it's going to look like this. And down here, it's going to be attracted to the South Pole. And right here, since it's in the middle, I'm going to have equal attraction and repulsion from both sides, and that means it's going to end up being parallel to my bar magnet. It's going to look like this. I'm going to get a similar one on this side too. You've probably done the experiment where you've shaken iron filings over top of a magnet in order to see the magnetic field pattern. Now, those filings tend to make lines on your page because if they're in the same direction, they tend to clump together. But it's really important for us to remember that these field lines aren't real. They're constructs to help us determine the direction the force would be on our little test compass. Those filings aren't actually looking for these lines that we're drawing, but rather have just kind of come together. Now these magnetic field lines, if I start to join them together, these are still showing us the direction a compass would be placed. I have some symmetry on both sides. Notice how all of these magnetic field lines, or field lines in general, have to start and end on our bar magnet. Using my test compass, I can see that they're leaving from the North Pole and coming towards the South Pole here at the bottom. So magnetic field lines will start on the North Pole and move to the South Pole. So just some general notes about field lines. Notice here I've drawn a gravitational field. Just like when I drew the magnetic field, they have to stop at my planet. If I was doing an electric field, they would have to stop on the charges. Field lines can never cross. If you remember, it's the resultant force we're looking at. So if I have more than one force, I need to combine them together and draw the resultant force of the two separate forces. If two lines are crossing, I have two different directions and therefore not the resultant force. One more thing to think about would be the gravitational field lines right here. If I took this area and I blew it up, it would actually look like this. At that point, these lines are so far away from the center of the Earth, if I actually looked at them, they would be almost parallel, giving me a uniform gravitational field at the surface of the Earth. This isn't just true for gravitational fields, it would be true for the other ones as well. And this is only due that they are so far away that even though they're radiating out, we would see them as almost parallel. We could also get a uniform field if I drew a parallel plates here, and I have positive charges along the top, negative charges along the bottom. The field lines would look like this. The positive test charge being repelled from the positive and attracted to the negative at the bottom. Any attraction or repulsion would be cancelled out by another charge on the opposite side, leaving us with a uniform field. So let's do some examples. Example 1. Gravitational field strength is 2 newtons per kilogram as electric field strength is 2. Now, remember, electric field strength is going to be force per charge. So I need to look for the unit for force, which is newtons, and then for charge, which is coulomb. It is not energy per charge, or charge per force, or charge per energy. Our answer is D. Example 2. In the diagram below, two identical spheres, A and B, have equal positive net charges. So remember, we use a positive test charge, and here it's going to be repelled in this direction. And then from B, it's going to be repelled again, but in this direction. Now, since these are equal charges, those two forces are going to be the same because we're also same distance away. That means this one's going to have a net force left and this one a net force right that are going to cancel out. And what I'm going to be left with is a net force just upwards in this direction. Looking at our choices, our answer is D. Example 3. Which diagram shows the magnetic field around a bar magnet? Remember, we're looking for the direction our little test compass will point. Its north pole will not be attracted to the north of the magnet, so that's wrong. This one, it's going to have to be repelled and move away. So that one's right, but this one's wrong. Now let's look at the south pole. It's going to be attracted to it, so this one's not correct, nor this one. It looks like C is going to be our answer. Let's check. Our magnetic field lines are starting from north, going to south. Yep, this is correct. So please check the success criteria here one more time so you can say yes to all of these points.